Hey, what's up? It's your old pal, Mr. Cook. We are going to go through, let's see here, I guess like number 19 only on this video, and then we'll do the other problems on the next video. Or no, maybe we'll go to number 20. Yeah, 20 or 19. I don't know. It just kind of depends on how long it takes to get through this one. All right, so let's see. Number 19, a customer at a gas station is pumping gasoline into a gas tank. The rate of flow of gasoline is modeled by the differentiable function g prime of t, measured in gallons per second. Selected values of g of t are given in the table below. All right, so here's our table. It says to use a Lefferts-Riemann sum to approximate the value of that function over that interval from 60 to 135 using intervals from the table. Okay, so we're trying to approximate that function. We don't know what the function looks like. We don't know what the function is. But we do know that, a couple of key points from up here. So we're going to use those points to make a graph. So let's see here. We got to do the interval from 60 to 135. So we're going to start at 60 on the x-axis and go up to 135. Okay, so let's just arbitrarily say that like this is 60 right here. And then there's 90 right there. And then 120 right here. And 135 right here. I know this isn't drawn to scale, but it doesn't really need to be. And then we've got points for 60, 90, 120, 135. Here are the y values that coincide with those x values. So we're going to write those up as well. Looks like the biggest number we get is 0.15. So what I'm going to do is just call this like 0.20. And then, just that would be 0.1. And then 0.15 and 0.5. And then I'm just going to draw the coordinates that I have. So at 60, it's 0.1, so right there. And then at 90, it's 0.15, so like right there. And at 120, it's 0.1 again, so right there. And then at 135, it's 0.05. I'm sorry, that should be a 0.05. Okay, and that's going to be right there. Okay, so Lefferts-Riemann sum. To do this, we only have these coordinates to work on. So we're going to break it up into these intervals here. From 60 to 90, that's going to be one interval for a Lefferts-Riemann sum. From 90 to 120, and then from 120 to 135. So we're going to make our rectangles from this, and using a Lefferts-Riemann sum, we're going to use the left endpoint for each interval. So for this first interval here, from 60 to 90, we're going to make this, this rectangle with a base between 60 and 90. And then a height is going to be based on the left endpoint. So it's going to go up to that coordinate right there. That's going to be our very first area that we're going to find, this one. Okay, so area number 1. And then we're going to do the next interval, and we're going to use the left-hand value for the height. So here's our base, and then here's the height for the rectangle on the left-hand side. So it's going to be this rectangle that we're looking at for area number 2. And then for area number 3, we're going to use for this interval the left value, which is just up to there. And we're going to use that rectangle. So rectangle number 3. Okay, then we just add up all the areas, and that'll be our approximation. We got to make sure, since this is a word problem, that we also put units. And we'll talk about how to get the units here in a second. Okay, so let's find our areas. Area 1, area 2, area 3. Now, before, all of the interval lengths, like the subintervals, right, like this one and this one and this one, they all were equally spaced, but now they're not equally spaced, so you need to be mindful of that. So you got to get the base length for all of these rectangles. And it's going to be different, like for the red one, right? It's between 60 and 90, so that's a base of 30. And then the height that we're going to find is, from our coordinate, our y value on the left coordinate from this guy. Okay, so since this coordinate was at 60, 0.1, that means that 0.1 is going to be our height. Then we're going to multiply it in a second. Well, let's do all these first, then we'll multiply and add them together, because I want to make a comment about that as well. All right, so for the second area, now the distance between the left interval and the right interval, 90 to 120, is again 30. And then the height is going to be based off of this coordinate right here, 120, 0.1. Oh, I'm sorry, 90, my bad. It's going to be based off the left one. So 90 and then 0.15. So 0.15 is the height for that one. And then last interval, let's see, from 120 to 135, that's a difference of 15. So the base now is going to be 15. And then the height's going to be based off of that coordinate right there, which is 120, comma 0.1. So 0.1 is the height for this one. All right, so now let's multiply them and add them together. Now, if I did want you to write out the approximation for this, you know, you write out 60 and then 135, and g prime of x dx, and then you'd write approximately equal to, and then you'd add the areas up. Now, on any other problem, I'd be like, yeah, just, you know, put these numbers and then just forget about it. So 30.01, or 30 times 0.01, 0.1, my bad, plus 30 times 0.15 plus 15 times 0.1, and then, you know, that would be your area. And you can leave it like this, but you always want to check the next problem to see if you're going to need that value for something, you know, to use. Because, like, let's say that we would use this, you know, the total that we get as like an initial value we would then need to take the derivative of. You wouldn't want to keep writing this long line of you know, of numbers over and over again. You'd want to just find like one number to kind of simplify it and keep moving forward. Let's see what the part B says. It says, using your approximation for part A and the fact that there are 6 gallons of gasoline in the tank at time t equals 60 seconds, find the amount of gasoline in the tank at time t equals 135. So that sounds like one where I'd have to use this, but there aren't like a lot of numbers here, so I think I would just still leave it like this. I would just, you know, have to get the units, and that's it. So that's my long number. That's my like approximation. And now let's talk about how to get the units. So when you have an expression like this, the g prime of x dx, right, it literally is multiplying on the dx value right there. So this is how you're going to be able to find the units for it. Find the units of g prime of x, and it says it in here. G prime of x is measured in gallons per second. Okay, so it's going to be gallons per second. And then you're multiplying by dx, and dx is going to be like, you know, the x value or the input value, which in this case is going to be t. Okay, so t is going to be time, and that's going to be seconds. And since what this, you know, what the integral symbol does is it's a summation of a bunch of values. It adds up a bunch of these like areas, right? This is the area unit right here. Okay, so think about it like as adding up a bunch of these, you know, gallons per second times seconds. And that means that when you add them all up, this is going to have the exact same units as this multiplication that you have over here. So if you just simplify it real quick, you know what the units are going to be. So gallons per second times second, the seconds cancel out, leaving it just in terms of gallons. So gallons are going to be the units for this one. Okay, and you can just leave it like that and move on. Next up, so again, part B, using your approximation from part A, so that number that we have right here, and the fact that there are 6 gallons of gasoline in the tank at time t equals 60 seconds, find the amount of gasoline in the tank at time t equals 135 seconds. So here's kind of like what this is implying that it wants you to do. Like, you're using this approximation to approximate like this interval for the accumulated gasoline. So this is like one of those start plus accumulation method problems, because if I write this out in the following way, like this integral from 60 to 135 of g prime of x dx, right? You know, if I were to complete this integral, like just do it by hand, I would need to find the antiderivative of g prime of x, would just be g of x. So from the fundamental theorem of calculus, this would turn into g of 135 minus g of 60. And what we're trying to do is find the amount of gasoline, approximate the amount of gasoline when t is equal to 135. That's exactly this right here. This is what we're trying to solve. So what we're going to do is add this part over. Okay, so this g of 60. Because what does the g of 60 mean? Well, the g of 60 in context means how much gasoline at time t is equal to 60 minutes, right? Is it minutes or seconds? Seconds. Okay, seconds. So if I just add that part over, g of 60, you know, which we know, we're told that it's 6 gallons. And then if I add that on to 60 to 135, this integral, then that should give me what I'm looking for, g of 135. But here's the issue that we have, right? We know what this is. This is just going to be 6 gallons, okay? But we don't know what this is going to be. Exactly. We know an approximation, and that's why it says to use your approximation instead of that, okay? So that's what we're going to use. We're going to use our approximation for this. So the approximation was all of this stuff, like right here, okay? So we're just going to rewrite it down here and then just leave it. So 30 times 0.1 plus 30 times 0.15 plus 15 times 0.1. And then all of that stuff is equal to g of 135 approximately. But change that from equal sign to approximately. And then we'll put the units on it as well. So we get this big number right here and then gallons. And I think that's all the work that you need to show. I'd be pretty content with this because it uses the fundamental theorem of calculus. It uses the approximated values that we have. And it also uses the approximation symbol because, these aren't exact fits. They're close to each other. Okay. All right. So that's number 19. I hope you enjoyed this video. I think that's it for this one. We'll go on to the next video and do 20 and all that stuff. All right. See you then. Bye-bye.